All right, please take your seats because in 1 minute we will have our next lecture. So you can slowly start preparing yourself to listen very carefully. Our next speaker is Karol Przybylski. He's the embedded Linux developer. He creates and integrates embedded systems for various industries. He gets great satisfaction from learning how things work under the hood. He publishes his experiments and guides on his YouTube channel. You can check the name of the channel in your application, where you can also rate the lectures and ask questions to our presenters. In his free time, he enjoys sailing and watching Blackadder. But the question for me to you, Karol, is can you do both things at the same time? Because it made me wonder a lot. Your favorite algorithm, Karol, is quicksort. That's what you told us. Karol, huge welcome on the stage. Big round of applause for Karol. Thank you.
Hello, everyone, and thank you for joining me on this lovely Thursday morning here at Code Dive. My name is Karol Przybylski, and this is Getting Started with Trusted Firmware for Embedded Linux. In this presentation, we have two parts. In the first part, I will talk more about the general architecture of the trusted firmware, and then I will show you how you can start developing trusted applications on your own. And I was already beautifully introduced by our lovely host, but some more things about me. I am mostly working with embedded Linux and everything that is associated with it. So Yocto project, build root, C, C++, everything goes. In the past, I worked on various projects. I also worked at Nokia on devices like this. This is probably ASIC or ASIL. And I don't know if you know, but you can actually buy them on eBay. Check it out. It's easy. More recently, I was working with set-top boxes. Those are little devices that you plug into your TV and you get Netflix, Disney, and whatnot. And also, I've been playing around with some mesh broadband solutions. And in my free time, as was mentioned, I like sailing. This is a photo of me from the last year Baltic cruising. And I also run a YouTube channel, which is fully committed to spreading embedded Linux knowledge. And let's go into the presentation. We have a problem in embedded system design because everybody wants to hack us and our devices. And unfortunately, operating systems and devices are getting more and more complicated. Every single device nowadays has to have Wi-Fi, Bluetooth, multiple operating systems. And as a consequence, the attack vectors are multiplying because the more complicated the system, the more holes you can poke through it. And we need to find a way, we need to have a way to protect our secrets. For example, keys used for decryption and encryption, logins, passwords, and so on. And one of the solutions is secure boot, which takes care of it on a component level. So each component in the boot chain verifies the next one, checks the signatures, and so on. And also security is not only a technical concern, but also bureaucratic one. Because we have Cyber Resilience Act coming, this is a EU regulation which is impacting software and hardware for various devices, and it's coming in full enforcement in 2027. And one of the provisions of this act is that security will be by design. So secure boot and other solutions will not be optional, but will be mandatory. So we have to ask ourselves a question. How can we do all of this securely? Protect our data, and limit the possibilities of an attack. And of course, we could try making it all only with software. Use containers and secure libraries. However, as the saying goes, there are 3 ways to program securely, and none of them work. So we have to have a hybrid solution. Something that is embedded in our processor architecture, and we can use it together with software to have a better, more stable product. And the answer here, of course, is ARM TrustZone, which merges software and hardware. And this diagram is the general architecture. Is the general architecture of trusted firmware. And at the beginning, this may seem daunting and very complicated, because it is. However, I can promise you that by the end of this talk, you will be able to decipher everything that is in here. And now let's examine some practical implementation of TrustZone and it is secure boot. But first of all, let's do a quick refresher on Linux boot process. First simple, and then I will show you the real hardware one. This is the boot chain, and we are starting from the ROM code. So this is the code that was programmed by the vendor in the factory. We cannot change it, or we cannot change it easily. And this is responsible for setting up basic clocks and loading FSBL. What is FSBL? First stage bootloader. And we are continuing initialization of the hardware, and we are setting up remaining clocks and initializing some external memory and loading SSBL. This is, of course, second stage bootloader. And here we can load the boot file system or boot with TFTP, show something like splash screen, and this could be U-boot, for example. And of course, the job here is to load kernel together with device tree blob into the memory and run it. Device tree is a structure that describes what hardware we have connected to our platform. And then we have Linux kernel. This takes over the initializations, loads up the drivers, and runs all the things that we need to make user space work. And at the end, we have the user space, and in here, we are running our apps, GUI, whatever. And our system is booted. And now, knowing those basic principles, let's examine the boot chain for STM32MP2. This is a board that is capable of running embedded Linux, and it leverages the power of secure boot. And it looks like this. As you can see, it's much more complicated. And at first, we can also see that there are some similar things here. For example, at the beginning, we have the ROM code, nothing changes. Then we have FSBL, first stage bootloader, checks out. Then we have U-boot, and then Linux kernel. So this looks familiar. However, there are several things here that are not. For example, TFA, this is Trusted Firmware version A for Cortex-A processors, so the processors that are capable of running Linux. And we will go through each of these, those acronyms and components so that you will understand everything about this process. But first of all, let's go to the explanation of what is non-secure and secure. Because as you can see, the basic boot chain was linear, one path, and in here we have the path that diverges, and we have two separate worlds. And so, to talk about the two separate worlds, this is an abstract representation of our system, both the memory and CPU state. On the left-hand side, your left, you have normal user space. The CPU is in normal state, executes instruction as always. You are using just normal memory that is assigned to your processes. And we have user apps like Netflix, GUI browser, running around, doing important things. And this is running on top of Linux kernel, which is responsible for handling memory and hardware. However, TrustZone introduces another world, the secure world, where the CPU enters secure state. So this is a different state than normal state, and it can execute secure instructions that are not possible to execute in a normal state. And also we have memory isolation. The user space apps cannot access memory that is assigned to the secure world. And also, we don't have normal Linux kernel running there, but we have something called the secure OS, which is, for example, Opti, and secure kernel. So this is usually RTOS or some microkernel architecture. So when you are running your system with TrustZone, you are actually running at least two operating systems. One normal for user space, and ARM TrustZone has separate one. And now let's answer the question how to switch our interaction between the two worlds, enter from secure to normal and the other way around. And it is done using software exceptions. So now let's explain what are the exception levels in ARM architecture. And when you look at it, you think exception level, it has to do something with the exception. But no, because it has more to do with privilege level. The higher the number, the more privilege we have. And on EL0, so exception level 0, we have no access to MMU, no access to interrupts, no access to kernel address space. We are heavily restricted, but that's good for our user space apps, and this is just our user space. EL1, so exception level 1, we can manage hardware, and we can configure the MMU, and you guessed it correctly, it is kernel. Kernel is running on EL1 exception level. And then we have EL2. This is an exception level where applications can manage guest operating systems. So this is hypervisor used for virtualization, very popular, especially in automotive. And finally, we have EL3, which is exception level 3, the highest privilege level. We can manage from this level all resources on all levels, 0, 1, and 2, the most powerful one. And this is called the secure monitor. And this part is responsible for switching between normal and secure worlds. And this is a diagram which further explains how this exception level plays with each of the worlds and various apps that we are running. And as I've mentioned before, the higher the number, the higher our privilege. And we have non-secure and secure partitions here. And on EL0, we have our normal user space apps running on one side. On the secure side, we have trusted applications which are handling our queries from the user space. EL1, those are the kernels, and on the side of the secure, this is trusted OS, something like Opti. EL2, this is hypervisor, trusted partition manager, and finally, on EL3, we have our secure monitor. And this part can change our context from non-secure to secure. And as a summary of exception levels, we can say that EL0 is like a baby, because normal baby does not have many rights, cannot do much on its own. And EL1 are the parents, because when a baby, a child, wants to play with hardware, like Xbox, it has to ask the parents for permission. And this is the same. User space application has to ask the kernel for permission. And on EL2, we have the government as a hypervisor, because hypervisor can manage multiple OSs, and government can manage multiple families and children. And on EL3, we have reptilians, the lizard people, because lizard people control everything, and they have ultimate power on all of the other resources. So those are the ARM exception levels. This you will probably not find it in the documentation. And this is the technical way of switching between normal and the secure world. So we have our application, normal application running in the user space. And for example, this application calls something like authenticate, because it wants to verify some signature, decrypt something, whatever. And we want to use the secure word. We want to use the ARM TrustZone for this. So we make the call to the library, and this is all happening on EL0, so 0 exception level. And then the library has a function implementation, it handles it, and then dispatches to the kernel. And how do we go from the user space to the kernel? This is done by assembly instruction called SVC. This is service call. And this is nothing else but a syscall. So we put SVC, then the number, and the syscall will be handled by the kernel. And this is happening on EL1 level, and then the kernel will dispatch our request to the TrustZone driver, which is capable of handling it and putting it further. Then we are switching from the normal to the secure world on the EL3 exception level, and this is done using the SMC instruction. This instruction is the most important on this diagram. It's called secure monitor call. And with this, our permissions are checked, and then we are going into the secure world. We are entering the secure CPU state, and we can use the secure memory. Then our call to authenticate is handled by the trusted application, creating keys, deciphering, authenticating, and the response goes back to our application's same path, but in reverse. So this is the basic of switching between normal and the secure world. And let's go back to this diagram. And most of the things now are explained, more or less. However, there are something that is yet to be explained, and those are those magic symbols BL2 and BL31, because we haven't yet touched on this matter. So this is taken straight from the implementation, from documentation for STM32. At first, when I saw it, I started laughing because it just looks like gibberish. BL2 loads BL31, BL2 loads BL31. It's clear, right? Of course. So it looks a little bit better on the diagram of the boot process. What is BL2? You have these arrows, loads, maybe or not, and calls, secure monitor call. It's pretty terrible. And I have no idea why ARM made it like this. I cannot find any mnemonic to remember what is BL2, what is BL31, 33, what are the differences. So I just make a quick dictionary for myself. You can use it as well, copy it, steal it, I don't care. But I have to explain it this way. There are no mnemonic device for this. So BL1, this is the first unchangeable code from the built-in ROM memory. We have already covered this. We can't really change it. This is usually made by the manufacturer. And BL2 is also a program within the trusted firmware, which is responsible for initializing the DRAM memory. And here, maybe the SOC vendor can influence it and change it. And BL31, this is probably the most important, is the secure monitor. This is the name, technical name for the secure monitor. It's permanently present, and it manages the switching between secure and non-secure worlds. And BL32 is the secure OS, for example, Opti, so RTOS, which manages our applications. And BL33 is bootloader for the normal world, usually U-boot. So having this dictionary, this diagram, and overall sequence makes much more sense. So now let's do a summary of the secure boot. Now we should know everything. So we are starting from the bottom. We have the ROM code and the first stage bootloader. We are doing the basic initialization, and this is happening in the secure world. Those programs have very small footprint. It's possible to load them using limited memory. Then we are loading the secure OS part so that then later U-boot and other components can use it, and for example, they can be used to verify all of the other components in the chain. So TFA BL31 and Opti. Opti is this RTOS which handles the calls from the user space. And then we have the SSBL, secondary program loader. This is U-boot, and then we can finish by loading kernel into memory. And once we have U-boot, we can set U-boot up so that it can verify the kernel image, for example. Check if it's signed, if it comes from the known source, and so on. And this is done using the TrustZone and the secure part of our system. And in case you missed anything, I made a video about this. So you can go, you can watch it. This is the same process explained more or less. It is in Polish, however, with today's technology, even in English, you can easily translate it. And now let's go to the second part of the presentation, and this is starting on your own. Let's say you want to develop trusted application on your own, how to do it, how you can start. And first, let's talk about the Trusted Execution Environment frameworks, which are also called T frameworks. And we have, for example, the Qualcomm QC. This probably you use it in your phones. If they have the Snapdragon, then they have the Trusted Execution Environment implemented with QC. For example, there is also Samsung Tigris, something like this. And also we have the third contender, which is Opti, which I already mentioned. And this is from Trusted Firmware. And one big advantage of Opti is that it is open source and it is recommended by the Trusted Firmware to use it. So this is our framework we can use when we are programming trusted environments and apps. And also, let me just remind that Opti is the software part, but hardware in all of those cases is ARM TrustZone. For example, Qualcomm QC, it also uses ARM TrustZone. And now we have the framework chosen, so now let's choose the hardware. And let's start good old-fashioned way with some requirements. And this hardware has to be supported by Opti, because we don't really have any other choice, because all of the other frameworks are usually closed source. It's not easy to work with them unless you have NDA or something like this. And the second requirement, most important, we don't want to pay hundreds of dollars for our board, so it has to be sort of cheap. And we need to have acceptable documentation and community support. This is very important when starting with something new, because we can have the best board in the universe, but without community, without documentation, it will be very hard to start. And as goes for the hardware which is supported by Opti, we can use the official list from the documentation, Opti read the docs. However, of course, this list is not up to date and you will not find everything that you need there. But you can play a little game of detective and check the maintainers file on the official GitHub. This also goes for all the other open source projects. The documentation can be so-so, but in the code, there will always be the answer. And my choice for the hardware to play around with trusted applications is STM32MP2. This I already showed during the secure boot demonstration. It costs about $100. It's not very cheap, but it's not extremely expensive as some other embedded Linux boards. And this hardware is really powerful. It has a lot of eMMC, a lot of RAM, and many, many features. But also you can try to look for other choices. The workflow will be similar. You can play around with Raspberry Pi version 3 and also Rockchip and NXP boards. And now we have the software, the framework we want to use, we have the hardware, so now we have to build the operating system for our board, and we have to build Linux for STM32, no matter how weird that sounds. And we will use the distribution package from ST, which contains build framework based on Open Embedded, so this is Yocto. Yocto is the most popular way to create dedicated embedded Linux distributions. And on top of Yocto, ST built OpenST Linux distro for Cortex-A. And also in this package, we will have the software for Cortex-M processor, because this board has not only Cortex-A, but also coprocessor with Cortex-M. So we will have embedded Linux running on Cortex-A, some firmware running on Cortex-M, and secure RTOS running in TrustZone. So we have 3 operating systems on one board, and this is the current trend of things. So you can see how this gets more and more complicated with time. And this is the diagram straight from the documentation, what is contained in the distribution package, a lot of stuff. Apart from kernel, we also have U-boot, firmware for Cortex-M, and everything. This is roughly how it looks like. And now let's do a speed run of Yocto build. So we download repo manifest from the site provided by the vendor, and the repo is basically a collection of all of the meta layers that we need to build our stuff that we want. Then we run Docker on our host to build it. I recommend running Docker always when working with Yocto, because satisfying dependencies for Yocto is absolutely terrible and almost impossible on your normal workspace. Docker is better. Then we initialize the manifest, setting up the build environment. Of course, the Linux way, some terribly long terminal command. And in here, we are specifying the environmental variables. So we want to build distro named OpenST Linux Weston. Weston is a graphical implementation of GUI interface. And thanks to this, we will also have some GUI available if you want to play around with it. And the machine, obviously, STM32 discovery. And then the script which sets up the environment. And at the end, we are building the software package by the command bitbake st image Weston. This is the image for the Weston implementation. And now we can talk a little bit about the examples of Opti applications, of trusted applications which are available. This is the directory, optiexamples.bb. BB files are the recipes for Yocto. This is basically a way of how something should be compiled and inserted into our system. But this version is too old. I tried building it, doesn't work. But fix is easy. Create new recipe with more recent opti release. You have to do it on your own. And then just modify local.conf with the 4.0 version. And then add simple image install append. This is the quickest way to do it, to check it out for yourself. And now let's talk about how the code for the trusted applications can look like. So this is the Hello World example from the official examples directory. And as you can see, we have a bunch of stuff in here. We have CMake lists, Android, and so on, for various build systems, different commands. This is the usual stuff. But here it gets interesting. We don't have one directory for our application, but we have two. First of all, we have the host, and then we have the TA. And the way the trusted application works is like client-server architecture. The host is a client, and the trusted application is a server, which handles client requests. So always the execution of the trusted application starts with the host calling appropriate function. And that's why we always have two parts, one host and one TA. And there are several methods which are obligatory to implement in every single implementation of trusted application and host. On one side, we have the host, which is running in the normal world, the user space. On the other side, we have TA, which is being run in the secure world. So everything starts with the function described by official API, initialize context on the host side. We are setting up just the context, the very basic stuff. Then we have to call the open session, also from the host perspective. And on the TA side, the function open session entry point is being run when this request appears. So this is also continuing of basic setup, the variables, whatever we need to do before the core of our application is running. And this is the core of our application. When we want the TA to do some real work, we have to call invoke command. And we are sending the command together with the memory buffer to the TA. And on the TA side, the function invoke command entry point is being run. Our request is handling, and this is the function where the real work starts. And once the work finishes, we call close session and then finalize context. And on the TA side, we have close session entry point and destroy entry point. And these methods are obligatory. It will not work if you don't implement all of them. It has to work like this. Always the communication starts from the host, the client part, and it is handled by the server, the TA part. And this is the code for the host application from the Hello World example. I cut some less important stuff from here, but those are the things that matter the most. And we have in the first line the define for the number of command. So we are sending the command in numerical form. For example, we want the TA to increment some value. And then we are setting up the structure with parameters and also setting up the value that we want to send to the TA. And I didn't include all of the previous methods because then it would be 50 lines long. But we are sending the command with invoke command, sending the reference to the session and the value of our command and the context that we earlier filled out. And then we send this, we wait for the return, we get the return, and then we can print it just using printf, still using the op.params parameter. This is how it works. This is how host will send command to the TA. And now let's take a look how the TA will handle this command. This is the function that is implemented on the TA side. As you can see, it takes as an argument the command ID and then the parameters that were being sent. And this is the implementation. And this is done using good old switch case. And it really looks like this in most of the cases. We just take whatever command ID we got, we check it, which function we have to call, and we call increment value or decrement value. For example, increment value, we take the param types, we fill them out, do whatever, and then turn it back. It would look almost exactly the same if we had a function check signature or something. We send the command, then the function is run within the TA, check signature or generate signature or whatever. This is how those calls are dispatched on the TA side. And in case you want to see me doing all of it on real hardware in real time, you can also check out this video tutorial that I did about this. This is from zero to finish about trusted applications and the implementation. And we might ask ourselves a question, but I am extremely lazy and I don't care. So what will happen if I ignore all of it? Well, it was already done. I'm sure you know Thermomix TM5. This particular device never implemented proper secure boot solution. And in case you don't know, this is basically a cooking device for people who have a lot of disposable income. And in the end, the lack of secure boot and some other software faults led to it that on this particular Thermomix, you could do rollback attack, so downgrade the firmware of the device to the version that was filled with bugs, exploit them, and run your whatever you want, the application. And in this case, this was done by Synactive, and they could just display their logo. They didn't do anything more drastic, but I think I saw that another product of this kind was running Minecraft at some point. So you have to take care of this because people will exploit it. And now imagine if your Thermomix or whatever you have would have camera or microphone, and it was hacked this way. Because this one doesn't, and the newest one also doesn't have the camera and microphone, but I think it's coming. You know, you dance and then the recipe is created based on this or something. This is the current trend, unfortunately. So if you want to have this, you need to implement some secure solutions. And now we are slowly coming to the end of this presentation. Let's end with some quick-fire questions. Can I program OPTI trusted applications using C++? No. What are the biggest restrictions when implementing trusted applications and similar programs? I was actually working for almost a year with QC framework as part of the projects we were doing for the checking of the DRM for a set-top box, and it is pretty restricted. For example, when you are writing the trusted applications, you cannot use normal C library, glibc or whatever. You get some C library, but everything that is not absolutely needed is deleted from it. So it can be really annoying to compile your application and so on, because you cannot use the normal calls that you would normally use in your application. And also the fact that most of it is closed source. So OPTI, for example, is something good because you can check out the documentation, there is community. But for example, for the TA which is running on your phone, Samsung or Google or whatever, it's almost impossible. You have to reverse engineer it or sign NDA with some company. And how you can debug trusted applications. You have to do it basically like this. There's nothing. There's no GDB. There's no journal. Impossible. Basically, you have to debug using print statements, not necessarily with this string, usually something else, and some kernel dumps. That's all you have available, and that's the tough reality. But this method is surprisingly effective. You can debug really most of the stuff using just the print statements. And the key takeaways from this presentation. Secure boot, a system, a solution which verifies each component using the secure world implementation in TrustZone. TFA and ARM TrustZone, this is the implementation on the architectural level of our processor of the normal and secure worlds. And if you want to start on your own, check out OPTI, try it, do some experiments. Thank you for your attention.
Now it's time for some questions. Please raise your hands if you have any. Karol, there are no questions to you. No, there's one. Brave one, thank you.
1, 2. 1, 2, 3. Yeah. Okay. Yeah. Thanks for the talk. You mentioned DRMs as one of the reasons why you would even need trusted applications. Would you mind, like, if we have the time, mentioning a couple more? Like, why do we even bother with this?
Yeah, the most important one is the Android keymaster, which is responsible for keeping the keys for encryption and decryption on your phones. Basically, if you have an Android, you have Android keymaster, and this is a trusted application, and it works like this.
Okay. Yeah. So basically, like, any time we have some secrets that we want to extract only like one way, basically, right?
Yes, because this is also important. For example, if you have a cryptographic key on your device, the key material is never visible in the user space. It is in the user space, but it is wrapped using the hardware key, and only the trusted application can unwrap it and do something with it. For example, sign or check the signature.
Awesome.
Yeah.
Awesome. Thanks.
Thanks for the question.
Is there any other? Okay.
How it looks like when we have few opti clients trying to open each session at the same time. I mean, what is the behavior of the opti application in Trusted Zone when we have a few session attempt at the same time? There are some kind of a scheduler of it, or it is done in multi-thread environment. How it looks like?
Usually the multi-threading is non-existent, but it will widely depend on the actual implementation. So usually the TA will take a very short time to execute because it's not doing a lot of computation or whatever. So I don't know the exact answer to this question when it comes to the Opti implementation. I know for the QC implementation, but I'm not allowed to say. But yeah, I would imagine that it would be a blocking call in this situation.
Okay, thank you. There was one more question, I think, at the back.
Oh, so I have a question about safety. Like, do you need any extra precautions to take when you are dealing with TrustZone? Like securing your memory buffers or something? Or you just trust the secure boot and believe that no one will tamper the key or anything you are dealing with?
You still have to take precautions because it is possible to break it still. However, this usually occurs still in the user space. So, for example, there was an attack which attacked a smartphone, Samsung S20 or something, which was using TrustZone at the time, and the attack was that because of the IV reuse, so this is initialization vector for some of the algorithms, it was possible to generate the same key twice and therefore extract the value of it. So when it comes to memory separation, it's pretty much rock solid, but still it doesn't guarantee you 100% safety. You still have to take care about this. Thanks for the question. Any more?
Thank you.
Okay, thank you very much. Do we have the last question here in the room? No? Okay, Karol. Thank you very much for the lecture. It was a pleasure to hosting you today. Thank you very much for the applause. Thank you. You can sit.